All right, so we're looking at another velocity versus time graph here. And the first part of this question wants to know the acceleration between A and B. Well, last week we learned that you calculate acceleration, average acceleration, by taking your final velocity, subtracting your initial velocity, in other words, the change in velocity, divided by the change in time. Okay, so all I have to do then is read the two velocities off the graph and the time off the graph and plug them into the formula for part A of this question. All right, so my final velocity is, according to the graph, 20 meters per second. Okay, my initial velocity is 0, and that takes 2 seconds. Okay, so that's going to mean positive 10 meters per second squared. Why do I need the positive on there?
Because acceleration can be negative too.
Right, acceleration is a vector quantity. I have to indicate that this is making the velocity more positive. Okay, it is in a positive direction. Okay, how many people have done B? Okay, I'm going to give you a little bit more time on that, but I will do this. Okay, if I want to find the displacement, that's average velocity times time for each section of the graph. I calculate that by finding what for each little part of the graph? Give you a hint, you have to draw some shapes.
Area.
The area, right? Okay, because each part of this graph, a different thing is going on, right? So between A and E, okay, or sorry, between A and B, we know the object is accelerating. Okay, so the average velocity would be half of the maximum velocity. Okay, then after that, we've got a rectangle, but what I'm going to do to save myself work is I'm going to extend that rectangle all the way to E. So I don't have to calculate quite so many shapes. Okay, after all, I'm looking for the total area under the line. Okay, and then I would do this triangle here and this rectangle on top. Okay, now you might have drawn slightly different shapes. That's fine, as long as you account for all of the area, you'll get the same number. All right, everybody with me there? All right, I'll give you a little bit more time then. Okay, if you're done B, keep going on C and D. Okay, and then we'll look at those as well. Look, there it is. That's what we did. All of that. All right, so for part C, we're looking for the acceleration between F and G. How long should that take me to calculate? None. Because what's the answer? 0. Okay, I know that that object is not accelerating because the graph is showing no change in velocity between F and G. Right? Its velocity is constant at 20 meters per second for that second worth of time. Right? That's very much a like multiple choice type of question. I've even thrown that in the written response sometimes for 1 mark on the unit exam. Okay, so test taking strategy. I think I've said this before, but if the question is out of only 1 mark, how much work should you do? None. The answer is right there. Okay, all you have to do is write down the answer. There should be no work at all. Okay, so if I gave you that question on a test, what is the acceleration between F and G for 1 mark? You would either write it's traveling at a constant velocity or 0 meters per second squared, and that'd be it. Okay, but I would catch a lot of people on that. Okay, they'd start showing me all these different calculations and what have you. Okay, that aren't right. Okay, that requires no calculation. Everyone follow on that? Okay. So for D, average velocity between A and F. How do I calculate average velocity? Total displacement over total time. Okay. So I already calculated the displacement to E. I just have to get the rest of it to F now. Agreed? All right, so that means 1 more triangle and 1 more rectangle, okay, to add on to 210. Okay. So this rectangle here is 2 on the base and 20 high. 2 times 20 is 40, divided by 2 is 20. Oh, sorry. What did I mess up? Something's not right there. 2 times 20 is 40. What am I messing up, guys? It can't be the same as this one.
It's 20 in the triangle and 40 in the rectangle.
Right, because I'm trying to, why am I dividing it by 2? I'm looking at the triangle and talking about the rectangle. Okay, 20 and 40. Okay, so I just have to add 60 to this 210. All right, so 270 meters divided by 10 seconds, it looks like. Okay, so that's going to give me positive 27 meters per second. Is the positive important?
Yep.
Yes. Velocity is a vector quantity. Okay, in fact, this should also be positive. Displacement is a vector quantity as well. Okay, and then for E, total distance traveled. Do I have a couple more shapes to put in there? How many more?
2.
2. Okay, I got to put in this rectangle here, which is going to be the same as the one beside it, so I can save myself some work. It has exactly the same dimensions. Okay, and then this little triangle that is 1 on the base and 10 high. 10 times 1 is 10, divided by 2 is 5. Okay, so add another 45. We got 315 meters for the total distance traveled. Okay, everybody all right with that one? All right, again, on a unit exam, would I give you a question like that? No. Okay, I would give you a question that had 2 parts, like a triangle and a rectangle, okay, something like that, okay, that you could do quickly. Okay, this one is just the same thing over and over and over again. Okay. All right, then. Okay, let's have you guys try this one. Okay, pretty much the same as the last one, just less to look at there. Okay, give you a few minutes on that one. Then we'll go back to a position time graph. Okay, so in part A, they want to know the acceleration between 7 seconds and 9 seconds. Okay, and we have to go back to that acceleration formula that's on our formula sheet. Okay, Vf minus Vi over t, which is also the slope of that line. Would you agree? Okay, so we've got Vf, okay, being 0, Vi being 3, and that takes 2 seconds. Okay, so if we do that, 0 minus 3 is negative 3 divided by 2 is going to give us negative 1.5 meters per second squared for our acceleration for that part. Is it okay that it's negative? What is it doing during that part of the graph? Slowing down, yeah. And according to the graph, it actually comes to a what? Comes to a stop. Its final velocity is 0. Okay, is it possible that it could keep doing that? Yeah, if it did, then that line would just continue down below the x-axis into the negatives. Okay, it'd be like running into a bungee cord. Okay, it would slow down, come to a stop, and then get shot backwards. Okay, the acceleration would be the same. Okay, how many people are done B? Okay, give you a couple more minutes, and then we'll go over B and C. Okay, so if we want to find the total displacement between 0 and 7 seconds, so that would involve that triangle there, okay, and then to 7 seconds we would have this rectangle, that triangle, and that rectangle. If you drew it differently, that's fine. Yeah. Okay, if you drew different shapes, like if you drew the small rectangle on the bottom longer, totally fine. As long as you got all the area accounted for, you're still good. Okay, so for this first triangle here, base of 1, height of 1, 1 times 1 is 1, divided by 2 is 0.5 meters. Okay, this rectangle here is 1, 2, 3 on the base and 1 high, so that's 3 meters. This triangle here is 2 high by 2 on the base. 2 times 2 is 4, divided by 2 is 2 meters. Okay, and then this rectangle here to 7 seconds, 1, 2, 3 on the base, and 3 high. 3 times 3 is 9 meters. Okay, so we should have there 11, 14 and a half meters, positive 14 and a half meters. Okay, everybody all right with that one? Questions on that one? Okay. Then they want the average speed over the whole trip. What else do I need to get average speed? I want to calculate average speed. What things do I need?
Total displacement and total time.
Close. Total distance, total time. Yeah, because speed is scalar. Okay, still going to calculate it the same way though. Okay, I'm going to look for that last triangle. I need that to get my total distance this time. Okay, since it's all positive, the distance and the displacement are going to be the same number anyway. Okay, all right, so this one is 3 high by 2 on the base, divided by 2 is 3. All right, so we add 3 meters, so I've got 17.5 meters as our total distance traveled, and the total time is obviously 9 seconds. Okay, so if we do that, we should get 1.94 meters per second. Okay, no vector on that, no positive because it's speed. Okay, questions on that one? Everyone's okay with that? Okay. And then the acceleration between 2 and 4 seconds. So that would be from here to here. Okay, acceleration is final velocity, 3, minus initial velocity, 1. Okay, that takes 2 seconds. Okay, 2 over 2 is positive 1 meter per second squared. Okay, guys, those 4 things are exactly what I would ask you on a test question. Okay, I would have a triangle and a rectangle, okay, or maybe even something like this that's not too terribly complex, okay, and I would say, you know, I'd ask you to do an acceleration calculation. I'd ask you to do an area calculation for distance or displacement. I would ask you for an average speed or average velocity calculation. Okay, that's the stuff I would ask. Okay, so just like that, wouldn't be any tougher than that. Okay. All right. Now, looking back at position versus time graphs, just as a quick review, because it's been a while since we talked about those. Okay. This is a position versus time graph. What is this object doing?
It's accelerating and then accelerating in the opposite direction.
Yeah, it's doing actually about 3 different accelerations here. Okay, it's actually slowing down during this first part. How do I know in this first part it's slowing down?
Because instead of going up like this, it's going over.
Right, it's going over, which means the slope is getting flatter and flatter. Right? If on a graph like this, if my line is horizontal, what's the object doing?
Staying still.
Staying still, because it's a position time graph. Okay, that means its position would be unchanged. So like probably for a little tiny bit of time right here, it might have been standing still. All right, then here, okay, it's curving away. The line is getting steeper. It's accelerating, but it's accelerating in a negative direction. Okay. And then for this part here, I can see that it is slowing down again. Line's getting flatter. Okay, so here's where you kind of remember a few things about position time graphs. Okay, and again, that's not something I need you to memorize, but on a position time graph, the steeper the line, the faster the object is going. So if there's a curve on that graph, you just have to look at whether the curve is getting steeper or flatter. That'll tell you whether it's speeding up or slowing down. Okay, so just interpretation of graphs wise, that could be an easy multiple choice question. Alistair. Okay, all right, so what I would like you to do here is, okay, so this is a position time graph. Let's just quickly see how much you remember about position time graphs. Try this one. It's pretty straightforward. Just so you can read these, this one's 250, this one's 500, and this one's 750. I apologize for how blurry that is. When these upscale to my 4K screen here, pictures did not upscale. So they're just garbage. Okay. And then this is 100, 200, 300, 400, 500 seconds, okay, on the x-axis there. Okay. All right, give you a couple minutes on that one. Okay, so let's have a look at this one. Biggest thing here is we have to forget well, not forget permanently, but forget for this question, everything we've been doing on those velocity versus time graphs, because this is not a velocity versus time graph, so we treat it differently. On this graph, we can tell where the object is at various points in time. Okay, so the first part says wants to know the average speed over the whole trip. If I want average speed, I need total distance traveled divided by total time. Well, I already know the total time. It's 500 seconds. Okay, so that part's easy. Now I need to get the total distance. Does distance care whether the object goes forward or backward?
No.
No, okay. So it goes from 0 to 750 here. Agreed? Okay, how far does it go here? Nowhere. It stays at a position of 750 meters for the next 100 seconds. Okay? And then it goes from 750 back to 0. So it went 750 and then another 750 for a total of 1,500 meters. Okay, 1,500 meters divided by 500 seconds is 3 meters per second. No vector on that because it asks for speed. Okay. All right. Average velocity between 300 and 500 seconds. Okay, well, average velocity looks a lot like the last thing we did, except now direction does matter. Okay, so I would go final position minus initial position divided by time. Okay, that's how we calculate displacement, final position minus initial position. Okay, and those two things I can read off of this graph because it's a position versus time graph. Right? What's my final position at 500 seconds? 0. What's my initial position at 300 seconds? 750. How many seconds between 300 and 500? 200 seconds. Okay, so negative 750 divided by 200, okay, should give me negative 3.75 meters per second. Okay. Everybody all right with that one? So we use that velocity formula a lot when we're dealing with graphs, especially irregular graphs. Okay. If we just had one single linear line, we'd use y equals mx plus b. Okay. But in this case, because it's all over the place, right, we use this one instead. All right. C doesn't take very long. What's the total displacement over the whole trip? 0. Okay, because we started at a position of 0 and we ended at a position of 0. Final position minus initial position is still a big goose egg. Okay, all right. Distance traveled in the first 200 seconds. Did I already calculate that? Yeah. How far? 750 meters. Okay. Does it matter that it went 2 different speeds to do that? Not at all. Didn't ask about that. Just asked how far did it go. Went from 0 to 750. That's 750 meters. Okay. How are we feeling about this stuff? Making some sense? Okay. So, like I said, our Thursday's lab is going to be on velocity versus time graphs and acceleration. Okay. So I'm going to give you a couple more questions to do with graphing here today, and then tomorrow we'll start acceleration. Okay. Just strictly using A equals VF minus VI over T, manipulating it, solving for things other than acceleration. Okay. And then Wednesday we'll be working on that, and then Thursday we'll be applying that as well as velocity versus time graph stuff to our lab. Okay, and then Friday we'll kind of see where we're at, but probably by the end of this week I'll be able to tell you when your unit exam will be. Okay, probably looking at the last week of classes. Okay, so somewhere between the 17th and 22nd, okay, of December, somewhere in there is probably where it will fall. I definitely want to get it done before Christmas. I don't want to finish teaching you stuff on December 22nd and have to test you when you come back from Christmas. That would suck, because then you have to study over Christmas. You should probably study a little bit over Christmas, but like not like because you have a unit exam when you first come back. Okay? As a suggestion, since we're on the topic, or I brought the topic up, over Christmas, this is what you should do for science. I can't speak to your other classes. For your science, start getting all of your stuff organized. Okay? Figure out where your chemistry stuff is, your biology stuff. Have a read over it, look at a few things in preparation for your final. Okay? We will have a very short unit when we come back from Christmas, global systems and energy. Okay? I've taught it in as few as 4 days. Okay? But we should have like 8, which would be awesome. And that's like just the right amount of time. Then do a little bit of final exam review, and then you have your final. So if you start looking over things just a little bit, okay, it doesn't have to be hours and hours over Christmas, but just get your stuff organized, quickly review a few things, that'll be a good start. Okay? Then things won't snowball on you, okay, in January. Because you know how you felt the last couple of weeks? That's how January feels. Okay, because you got finals coming up, everybody's bringing in their last things, and you got English, you'll have your final paper and all of that kind of stuff. Okay, all of that, it gets really busy again there in January. So you want to have a few things organized over Christmas because it'll make your life easier in January. Okay. All right, so what I would like you guys to work on page 7 of your digital workbook, okay, you'll find this thing that says kinematics assignment number 1, okay, and it's got this position versus time graph, and then if you scroll a little bit further, okay, there's some questions to do with that. Some of them are very, very simple, like just reading the position off of the graph, like question number 1, okay? And then after that, there's a velocity versus time graph, okay, with a few questions on it. Okay, so it'll be kind of the last thing. It's not coming in for marks, even though it says assignment, it's not coming in for marks. Okay, what I would like you guys to do for that first graph is I would like you to do number 1, number 4 and 5. So 1, 4, 5, and 1, 4, 5, 6, and 8. 1, 4, 5, 6, and 8. Okay, there's only question number 9 on the velocity one, so do it. Okay, and then we'll go over those as time goes by here, okay? Okay, so I'll leave the graph on the board here, but you're probably better off to call it up on your phone so you can zoom in and see where all the points are.